everybody for joining, whether you're here in the room with us in Durham or online. Today we have graduate student Kelley, who I know a little bit better. He's working in the SuperDARN lab here in Space PT, and is going to show us a few things about SuperDARN data and something you can do with it, along with what TEC data, kind of some interesting science with that. So without further ado, I'll flip the video over to Ian, even though it'll sound like I'm talking or my name's there, but it's really Ian. Take it away.
Okay, thank you so much for the introduction, Ben. Hopefully people can see my screen. My presentation is called MSTIDs in TEC and in SuperDARN. So, introduction. What? There we go. Sorry about that. Hopefully people hear me. So what are MSTIDs? Traveling ionospheric disturbances is what the TID acronym stands for, and medium scale or mesoscale is where the MS comes from. It's basically a wave in the plasma density of the ionosphere. I mean, it's very common for us to see these with a lot of different data sets, but SuperDARN, it's common to see these in SuperDARN, especially during the day in the winter. It's the most common ionospheric disturbance in mid-latitudes. And so why it's important? Well, ionospheric disturbances are the leading cause of GPS navigation errors. Understanding MSTIDs also allows us to better model HF propagation, because as you can see from the SuperDARN HF radar, the returns are, you can see the signatures in them, so they will affect HF propagation. MSTIDs are caused by natural disasters sometimes. They're caused by weather events, such as polar vortexes cause them. There's ongoing research about the Tonga explosion that happened last month, which caused MSTID behavior. Starting in the South Pacific, but really globally, you see the signatures of the waves. And these have been studied for quite some time observationally, first using ionosondes. This study would use coherent scatter radar, SuperDARN, as well as GPS total electron content. I look at those two, but also some other studies may use aerial imagers, incoherent scatter radars, etc. So let's talk about what SuperDARN is. It's a coherent scatter radar, and it's a global network of these radars actually. So it's there's many of these covering the northern and southern hemispheres at high latitudes and at mid latitudes. I think all of the data in this presentation is going to be from radars in the continental United States and in New Zealand actually as well. So here's a picture of what SuperDARN is on the upper right hand corner. That is the more old style of antennas. Those are called log periodic. Basically, you have 16 of these antennas in a row, and then you have like a couple more, like more out front to find elevation. But you have a bunch of these, and it's a phased array, so you can electronically steer the beam of the radar. And the main purpose of these radars, among other things, is to sense plasma density irregularities in the ionosphere. So you can see we have what's called a ray tracing path at the bottom. The pink lines are the magnetic field lines, and we need to have the ray paths be orthogonal to the magnetic field lines for the scattering condition to occur. You also need the irregularities to be around half the wavelength of the signal. And so we get returns from the ionosphere where there's plasma density irregularities. We also get returns from the ground, which is the most common SuperDARN return. That's called ground scatter. And you can see it's actually over the horizon when it happens usually. So this would go out to 2,000 kilometers, which is really far. Considering you can't see that then also there's an ionized meteor trail layer at about 100 kilometers. SuperDARN can use that and actually study some kind of neutral stuff. And sometimes we see things from the E region, F region, and ground scatter change based on what's on the ground. For example, if it's like ice, you may get different returns than if it's water. So let's talk about SuperDARN data. There's like 6 measurables. You can also measure what time it occurs, but the main ones you would look at would be like power. And so that's the power is like relative to the noise floor. It's measured in dB, typical value 0 to 40 dB. And that's just a portion of the original power scattered off the target. And then we just measure this relative to the noise floor. The Doppler velocity is whatever the radar hits. If it's moving towards or away from the radar, it will put a Doppler shift on the frequency. And usually if it hits the ground, it's basically 0. But if it hits a plasma irregularity, it may be going up to 2 kilometers per second. So we see a really wide range of Doppler velocities, and we use the Doppler velocity to characterize what kind of scatter it is. The slant range, the radars can go pretty far. I think most of the data I'll be showing is within 2,500 kilometers. And the resolution is generally 45 kilometers. So the way that that's done is you transmit a short pulse sequence that you know, and then you measure the range and also the uncertainty of the range, you know, based on the pulse. And then you can get basically the range of the echoes. And then also you have elevation angle. As I mentioned, there's a second array. It's called an interferometer array. And they're just for C only. And so then if you know the distance between those two arrays, the frequency, you can estimate the elevation angle based on the phase shift between them. I'm not going to be using that data for this, basically things like highlighted drill using. And then azimuth, I mentioned it's a phase array system, so you can electronically steer the beam because of interference between all the beams. If you impart a phase shift, a constant additional phase shift on each successive beam, steer the beam, you can do beamforming. So the beam is a lot narrower than if you had just one beam, for example. So yeah, you can steer the beam to about 3.24 out of a total of 50 degrees in azimuth. And then spectral width, sometimes there's an uncertainty in the frequency. And the physical explanation for this would be like if there was like a spread in the velocity, the line of sight velocity of the target or something, it would spread the width of the Doppler of the spectrum of the transmission. But again, only really the top 3 of them focused on for this study. So what does SuperDARN data look like? The lower left is an example of a range time intensity plot. So you can see we have power in the upper panel, and that's in dB, as I mentioned in the previous slide. And then in the lower panel, we have velocity, which you can see in meters per second. And a lot of it is gray, which means it's been identified as having a low velocity, or just for various algorithms that SuperDARN has, saying that this is pretty confident that this is ground scatter, and the velocity should in fact be 0. So yeah, you can see this is not 0; it's like negative 150. So this is significantly different. And so this would be called ionospheric scatter, and then this would be called ground scatter. So then, based on, you can take a snapshot of time, basically. So you can take like a 320 UT here. It would be like here, and then you would see kind of we have some stuff close into the radar that's called meteor scatter. You can see that over here. See this red band is the ionospheric scatter. This is called half-hop because it basically goes up to the ionosphere and it comes back to the radar. You can see we have ground scatter. So it reaches the ground again. That's called one-hot ground scatter. So it goes up, it refracts off the ionosphere, and then it returns to the ground. So you can see all that happening here. You can also see a velocity gradient in SuperDARN here. And so if you have that, you can basically resolve the velocity. You can kind of tell what direction it's moving, especially if you have 2 radars, which is where dual SuperDARN comes from. You can resolve the velocity vector. And then from that, basically, if you know the background magnetic field and you know the velocities of the plasma irregularities, and you assume that the motion is E cross B, you can create a map. So that's kind of high level what SuperDARN does. But this study will be focusing more on MSTIDs and SuperDARN, which is kind of preview of that. That's this little squiggly line here that you see in the concept. So let's talk about the other data set. It's called GPS total electron content. And it's derived from GPS or other GNSS constellations. Specifically, if you have two frequencies, the pseudo range, if you transmit what time the transmission occurs and then measure the path, the delay, you can have what's called the pseudo range, which is your estimate of the range between you and the satellite. And there's some uncertainties based on the aliasing of the phase of the signal. But it's a good estimate for how far you are from the satellite. And if you have two frequencies and you get two different answers, well, the delay is actually a function of the refractive index between you and the satellite. So assuming that what's between you and the satellite is not free space, you can estimate the refractive index if you have two different frequencies. And that's what GPS TEC does. And it's basically a line of sight measurement between you and the satellite. And so the units are electrons per meter squared. So you assume that the refractive index is coming from 3 electrons, and that these electrons, you can measure the electrons, but you can't measure the density. You can only measure the column density. So that's why it's over an area. It's the geometry on the lower right. The receiver, the satellite, is at 20,000 kilometers above the Earth's surface, and you just basically assume that the electrons are in a very thin layer at around 300 kilometers. And then if you assume that, then you can use TEC as a proxy for electron density in the atmosphere. So TEC comes in TEC units, generally 0 to 50. So it would be like 1 TEC unit, 10 to the 16 electrons per meter squared. To assume it's a very thin layer. Thin layer assumption allows you to basically map this to a single latitude longitude point on the Earth's surface. And then you have the time of that, and you basically have a measurement of electron density in the ionospheric. So there's a lot of TEC data, and the best way that I found to use it is through the SuperDARN Magical database. It comes in 2 different formats. The most commonly used is low resolution, which comes 1 degree by 1 degree latitude longitude bins with a 5-minute time resolution. And one issue with this is that a 1 degree by 1 degree bin will change its area based on what latitude you're at on the Earth. Another issue is that sometimes we need higher resolution. And so they have a higher resolution data set that's actually downsampled to form the low resolution data set. And you can see that's on the right. And so it's pretty intensive to just look at it. I mean, that's a pretty cool animation. But I just made that to show like, what it looks like. And you can see you have thousands and thousands and thousands of individual. Each point is a satellite receiver pair. So you have thousands just over the US. And these wave fronts you see moving across, you can see that. That's when the satellite comes within view of the receivers. And also, I should say that anything with a low elevation angle is thrown out. You don't want any oblique paths to the ionosphere. So as you may expect, for MSTIDs, TEC would be a really good tool to use. And you can actually kind of see one here. You can see a lot using this data set, especially if you use a high resolution. The challenge is that the data set's really dense. So let's talk about the processing needed. In many cases, you need to detrend the data. So the plot of that will be on the upper right. So this is over like 4 hours. You can see the TEC. This is the raw data up here. And there's like a big variation if it's like with the time, local time, things like that. And you need to throw that out in a lot of cases to pull out very minute details in the TEC. So you would take a rolling average and you would subtract it. The problem, of course, is that there's like 30,000 rolling averages to subtract. And if each one takes this plot, maybe took 5 to 10 seconds to make, if you multiply that by 30,000, you quickly you're going to be spending a lot of time running the code. And the data files come like 10 gigabytes. It becomes the whole world for one day, like a ton of data. And then you clean it, everything goes out to like 6 decimal points. You clean it, But even then, it's still like half a gigabyte or 1 gigabyte just for like 4 hours over the US. And again, that's because there's like 30,000 individual satellite receiver pairs at any one time. So every 30 seconds, you get 30,000 more data points. So what you do? It turns out that the way that some of the Python libraries are written, it's way easier to detrend a data set that's 30,000 times as long. That's just one data set than 30,000 short ones, which I did not understand at first, but it just makes it much, much faster. It takes like 10 minutes to do this, whereas it would take days. So I downsample the data to only include 2 satellite receiver pairs. In reality, there would be 30,000 of them here. But you can see the data comes sorted alphabetically by satellite receiver pair and then by date time. And so you get like 30,000 data entries just for 22, 30, 30 here. Hopefully you can see this. And then the next 30 seconds will come and you get the same thing. And so the way that I can trend it is instead of sorting by code, I sort by the date time. And then I sort by the code. And so you just throw out the ends of it, and there's still enough data, but you just detrend it as if it's one satellite receiver pair, but it's really 30,000. Anyways, I just wanted to talk about the processing a little bit. This took me some time to get to. Get a much faster detrending. So I did not come up with this. There's lots of studies that use detrended TEC, and I basically use these studies to make sure that my algorithms work correctly. So here's an example of a paper, Zhang et al. 2019, showing a 30-minute detrended window for a TEC event over the US. And basically, this is my take on it. So this would be like the upper left window here. And you can see kind of like a horseshoe effect here, and you can see it here. And basically, I just worked on these algorithms until it looked pretty similar. And I was like, okay, good enough. This takes like 15 minutes, whereas I know their algorithms may take days to run because they resample the data, and it's a better algorithm, but I guess it's a trade-off between how fast you want to code. And then again, it's like an algorithm problem, so it's not like a faster computer that you're gonna help you. It's just you have to be creative with how you code. And I can fine-tune parameters as well. I can change the rolling average period. So this is 30-minute rolling average, 15 minutes per hour, or anything like that. But the point of this is that you want to detrend the TEC by subtracting a rolling average in order to see behavior such as MSTIDs. So I'm calling this TEC darn. I'm not sure if that's accurate, but how do we compare the two data sets? Well, basically, you take a SuperDARN RTI plot and you take a TEC plot, and you just you draw over the TEC what the radar would see. So you draw the mean of the radar, and then you see if any of the points are within the mean. And then if the point is within the mean, you measure the slant range that it would have to the radar, and then you just plot it on an RTI plot. So the effect is if one of the SuperDARN radars could see TEC, which of course they can't, but I want to compare the two data sets as closely as possible. So this is the method I came up with. I should note that I'm using geographic coordinates because the TEC data points are moving every 30 seconds. They're moving to a different latitude, longitude. They're float values. And so it would just be really intensive to convert any of this to a different coordinate system. But here's the approach I have now. So you can see this is TEC on like a SuperDARN RTI plot. And then this is the same SuperDARN RTI plot. Oh, and yeah, here you go. So this is a snapshot of time, 1 o'clock UT. So you can see that it's like purple, and then it goes yellow, and then there's a line of coverage. And right here, what you see is purple, and then it goes yellow, and it's one coverage. So you can see that how the RTI plot kind of matches with what, not a scan plot, but like a global map of TEC, which is interesting. And it provides us a good technique with studying MSTIDs because you can see two sides of the same thing in two different data sets, but right on top of one another. So let's talk about MSTIDs some more for a little bit. The original kind of classical thinking is that these are tied to atmospheric gravity waves. So a gravity wave would be like, for example, waves in the ocean are gravity waves. And so the gravity is the restoring force, and then you have the force, and then you basically have a wave in the neutral atmosphere. And this also causes the ions to behave in a wave-like nature, go to a different altitude because of ion-neutral collisions. But as altitude varies, so does the recombination rate. So you will get an electron, you'll get the wave in the electron as well. And that's kind of the classical thinking of how you see TIDs in the electron. So things like polar vortex, explosions, joule heating, these cause gravity wave-driven TIDs. And so the distinction is that I'll talk about the distinction on the next slide, but yeah, these are more common during the daytime, in SuperDARN, during quiet times, and also at higher latitudes, maybe. So if that's the classical way of looking at things, what is the alternative? It's called Perkins instability. Basically, it has to do with the electric dynamics of two different regions of plasma varying altitude. You assume that the current between them, the tangential current between them must be constant, divergence free, not constant. It must not have, no divergence, basically. And so you have to have, so they have varying densities, which means they have varying conductivities, and so you get varying electric fields to make up for the fact that the current between them has to be the same. And so then you get electric fields in different directions, but then you have so then you have gravity is force, and then you have the cross product. Electric field must be 0, and so then you have basically a solution where you get a positive growth rate for plasma stability. So what's distinct about these is that they have polarization electric fields, whereas an atmospheric gravity wave-driven TID do not. And so one thing is that you will get conjugacy between hemispheres because the field lines are conductors. Another thing is that they will generally go westwards because the instability has a reliance on the field geometry. So in the northern hemisphere, we generally see westwards TIDs because the other directions are dammed out. And there's the figure kind of showing the two different plasmas. So let's move toward observation. This is an event. This is a very significant event. September 7th, 2017. But yeah, here's the geomagnetic conditions. This is pretty significant. Yeah, so these animations I made, it's very cool to see actually. You can see how things move westwards, you can see the waves. You can also see that the TEC like -1 to 1 is a pretty high scale. So here's the animation. There's a lot going on. These are just cool to watch as well. A couple times, it's not fast. Hopefully this shows up on Zoom. I know sometimes videos don't look good. This last time. But yeah, you can see a lot of like wave-like structures. And again, this is detrended 30 minutes subtracted. You take the rolling average of the T subtracted. Okay, so during the event, there's a strong correlation between the two waves. So again, this is where I'm showing you TEC as a SuperDARN consensus on an RTI plot, and you plot them on top of each other, and surprise they match up, at least in this case. And it's a positive correlation in this case as well. You can see we have, this is just like from this box, we have THC in red and SuperDARN power in blue. And the SuperDARN power goes positive when the THC goes positive, and vice versa. And you can see that the power matches with the yellow on this map. And so, yeah, it's pretty good, which was maybe not completely expected that it would be this good of a relationship. So from this, you can annotate these plots, you can estimate the velocity and applied wavelength. This is the line of sight velocity, so this would be like moving using the slope. So basically, if it's at 2,000 kilometers at 15 UT, or at 0.15 UT, and then at 1 UT, it's at 0 kilometers. Well, figure out what that is in meters per second. And then you can measure the distance to find the wavelength, the period, and then, yeah, that's how you do it. And basically, these are in matplotlib, so you know the slope and thing, you know the vertices based on your annotations. So I basically just drew lines. So the data sets are pretty similar. How similar are they? Well, I did this process where I kind of draw lines, and then I copied the lines from one and pasted them onto the other, and they match pretty well sometimes. Like, for example, these three lines were drawn on the TC, and then I just copied and pasted them on the same vertex locations on the SuperDARN. You can see some pretty good matchups. Another thing I did here was I found the location. Actually, it's a pretty individual location where Crystal Sally, a radar in Oregon that looks eastward, and a radar in Virginia that looks westward, at the same slant range for both radars, see same thing, same location. And that location is like 99 west, 46 degrees north. And that would be at like 1,800 on both plots here. So we're seeing two sides, literally two sides of the same thing in two different data sets. And then from this, you could, instead of measuring the line of sight velocity, you could actually arrive at the velocity of the TID itself with some pretty good certainty, because you're seeing two completely different radars, two completely different sets of electronics. And yeah, you see it in the TC as well. So that's exciting. Another thing I mentioned conjugacy, there was one radar operating during this event. And it was in New Zealand, and it was looking kind of westwards. It's called the Unknown radar. But as you can see in the lower right-hand quad, the TEC coverage, this is like one of the most remote locations in the world with the Southern Ocean. So you would expect good coverage anyways. So I don't have TEC for you for this, but it did see signatures in the Southern Hemisphere. So, and they were faint, and they were going westwards, which is interesting. So the ones we saw in the Northern Hemisphere were very similar to this. So that's kind of suggestive about what's going on here that you see on the measurements. Again, this radar is like not perfectly conjugated with the plots I was showing, but this was basically the only one that was running in the Southern Hemisphere that we could data for at a reasonably low latitude. Yeah, so this is in New Zealand, looking southwestward. As you can see, B1 is being here. And the signatures that you're looking for, they're kind of hard to see here. It's this kind of thing right here. It's these like solid lines. And these are occurring at around the same time as well, like 1 or 2. So they're faint, they're like 20 to 30 dBs, but the carrying power across radars is maybe not so good a thing to do. But the point is they're much fainter here, like 20 to 30 dB down. Whereas these are like right here, that's a 40 dB. But you can't really compare across radars too well. Okay, so I have another event for you. I'll go through these a little faster. But this is basically the same thing, different event, just to show you that this is not just an isolated type thing. So here's another movie. Oh, why do we need a full screen of this? And I rendered this. I rendered this at too slow. This too fast of a speed. Another thing you'll notice is the coverage isn't so good. maybe like 10,000 data points you're looking at versus like 30,000. And the reason for that is there's just less coverage in the data files for some reason. 2015 to 17. But the West Coast is really good, as you can see. Right over time. But yeah, again, you can see westwards traveling ionospheric disturbances. This is a KP7 event, so not as strong, but still kind of considered to not, certainly not quiet time. You can see the same kind of thing happening, maybe at a slower speed. Yeah, especially over like the western portion of the United States, the coverage is really good. This is pretty exciting. This data set is so much from it. Basically, it just doesn't so dense. If you can deal with the fact that it's so dense, you can get a lot from it. Let me know if you want to see the movies. Yeah, they're pretty cool. So yeah, here's the geomagnetic conditions for this event again. But yeah, we still see the same kind of thing. This beam actually, here we go. Christmas Valley West beam 8. So this will be a beam in Oregon. And I like to use this beam a lot because for these beams a lot, these specific ones, because they look basically along the coast where there's actually a lot of receivers. Whereas if you go inland into Canada and Alaska, there wouldn't be as much. So you get almost okay TEC coverage like around this region here, which would be like up in here. Whereas you wouldn't get that if it was looking this way, which is why I chose to use this beam, even though it's like kind of way off to the west, kind of looking towards the bay side actually. But yeah, we still see this is moving away from the radar. This is a westward looking radar, so this is still pretty consistent with westward propagation. You can see the striations are really, really strong here. This is plus or minus 3 TEC units, which just for reference, the background might be like 20 to 30 or maybe 50, but this is like around 10% maybe of the background value, which is not typical of some MSTID. Sometimes you have to crank this up, and this axis would be like negative 0.1 to 0.1. So this is like over 10 times the axis that you would use sometimes. So it's very, very strong, and also the SuperDARN power is pretty good. And they match up pretty much 1 to 1. It's actually surprising how well they match up in this case. I should point out that both events I've shown you so far during the summer, during high geoactivity times, and kind of towards the dustward sector, although this one's a little more towards the bay side. Yeah, so the bay side is over here. And then I did a similar approach with this. I did a similar approach here where you take the 2 plots, you annotate them. You annotate them using the vertices of the times and the ranges, and then you just copy the vertices from one annotation to the other, and the match is pretty good here. You wouldn't even like just looking at some of these plots, you wouldn't know that these were drawn not on the TEC. Like that's how well they match. And it's not this good in all cases. This event's really good. So yeah, great match, westward propagation. So Christmas Valley east beam 19 is looking pretty much eastwards, northeastwards, towards the radar. It's going this way. The range is reducing the time. And then Christmas Valley west 8 is looking more westward. So it's looking more. So yeah, the velocities are pretty consistent if you take into account the radar's directions. Plots. So let's talk about how SuperDARN can be seeing returns and how we know why TEC is seeing MSTIDs, but why is SuperDARN seeing MSTIDs? So for the classical SuperDARN TID behavior going back like almost since the beginning of SuperDARN, it's thought that you get like density fluctuations in the ionosphere, which is what you see here. And then that is going to cause the rays to focus and defocus because these are going to have different refractive indices. So like the higher density is going to have a higher refractive index. It's going to turn over. faster, and the effect is when you have ground scatter, eventually when it goes, it hits the ground, it's going to be focused. And so you're going to get areas of focusing and defocusing. And so kind of the atmospheric gravity wave approach is that it's pretty much ground scattering you see. So very low Doppler velocity of superdarn. And the other problem is that if you're trying to view this from a TID lens, you want to map it to a lower range, not half the range, but you have the slant range, and you want to map it to half the slant range, or wherever it turns over. That you're trying to measure the TID. So you would expect if you have superdarn measurements, the superdarn measurements are going to be roughly, or if you have TEC measurements, they're going to be roughly half of where you can see the superdarn measurements to be. If this is the dominant region, focusing, defocusing, because the superdarn measurement is going to come from way out here, whereas what's observing is up here, and that's what the TEC observes as well. And so here's the equation for it. Basically, you have the height of the ionospheric layer, slant range, radius of the Earth, and then you want D, which is called like the map range. So you want to map into a short range. So initially, when working with the data, I thought that this was going to have to be done because I thought that this was the reason why we were seeing how we would see the matches between the two data sets, and that's pretty much not true. Everything I've shown you so far, this is not. This is just take the superdarn range to get. So this is maybe suggested that this is not the method by which the superdarn is generating returns from generating signatures from TIDs. Because this is kind of a classical MSTID quiet time observation. It's very common. In fact, it's so common. I took this data from like 2 weeks ago. This was just I log on to the superdarn website and I pull up the most recent data. Bam. It was MSTID right in the face. I don't have a velocity plot here, but it would be ground scatter. Pretty much this is daytime ground scatter. And you can see that, this is a longer period as well, maybe. So long plot is like, so the period of these would be like more towards like 30 minutes type thing. And yeah, you can see there's a periodic kind of focusing, defocusing effect. So then what you would do, this would be range. And that's kind of assume that this is focusing the name. Whereas what we're seeing might not be. So, here's some reasons why I think it's not. The first reason is I showed you conjugate measurements. So I mentioned that there's a polarization electric field in the electrified TIDs. And so if you see conjugate measurements, that's pretty evident that there is a polarization electric field. The other thing is I have a velocity plot on the upper right, and the velocities are very, very strong, 400 to 500 meters per second positive in this case. And that's the opposite of what like ground scatter would be, basically 0 meters per second. So this is pretty, you can be pretty confident that this is ionospheric half-box scatter. Yeah, this is also, I mentioned you can map it to a different range. So I did that, and it just looks like basically not good right here. Whereas if you map it to the true range, it matches up much better. This might not be the highest resolution plot. Again, you can see that these match up pretty well. And I've shown you this plot in this presentation like 4 or 5 times now. And it matches when you use the true slant range. It doesn't match when you map it to a reduced range. So that's another evidence that it's probably not focusing ground scatter. And then the other thing you can do, which I haven't included here, is you can ray tracing. If you really want to be sure something is ground scatter, you can reference ionosphere, you can do ray tracing of superdarn, and it can kind of tell you, okay, you expect ground scatter for this frequency, this ionosphere, this range, at this time. So there's a lot of different ways we can use to show that this is not focusing ground scatter, this is something else. And there's been some papers that have shown this, but this is kind of the only study that I know of that does this for storm time events. So let's talk about electromagnetics and why we're seeing the velocity variation that we're seeing. So here's the radar. It's looking north is up. The radar is kind of looking. This is 4 days west of 18, so this is kind of looking northwest, but more north than west. So this is a single beam of SuperDARN radar. That's what you can see. So yeah, so we have a background electric field because this is a storm time, and this is kind of the dust region, and there's SAPs going on. So we know that the background electric field is probably northwards, and then we also would imagine that we have winds. We have northward neutral wind. So the U cross B is the neutral wind. U cross B term will be westward if you have magnetic field into the page. You have westward electric field component, neutral wind. And you also have a northward electric field component. You add these together. And this is like, we're just assuming that this is the dominant electric field in this case, but you would assume a northwestward electric field in this case, which is this vector right here. This is the background field, so this is not plus U cross B. And then we know because of TEC and there's a TID going on that we have variations in the electron density. That's shown here. We look at high electron density, low electron density, high electron density star. And so this will affect the conductivity term. And we know that current is conductivity times electric field. But as I mentioned before, the current between the layers has to, there can't be divergence free, so the current has to be constant between the layers. We can't have sources within. And so what this means is there's going to be an induced polarization of electric field in the direction perpendicular to parallel to the direction of TID propagation to compensate for this changing conductivity term because we don't want J to change. And so there will be an induced electric field. So in the case that there's a high TEC, you'll get a polarization electric field kind of in a different direction in the background. And in the case where the conductivity is low in the depletion region, you will see an electric field kind of adding to the background field, the polarization field. So you get this flip-flopping of the polarization electric fields that you can see that I've drawn here. And this is guessing that this is the dominant electric field driving plasma instability, polarization. And from SuperDARN, you know that D, well, this is the northern hemisphere, so the D is roughly into the page. And then in SuperDARN, you assume that the velocity is in E cross B. So you take E cross B of this polarization field, this magnetic field, you get a velocity going this way, northwards. And then for the depletion region, you get a southwards velocity. And then you get a flip-flopping of velocity. And depending on your radar look angle, because remember the radar can only sense line of sight velocity, you're going to see a flip-flop or some kind of variation in the radar velocity itself. And here's an example right here. It goes negative 500 to 500 within like 1 minute here. This is pretty intense how it's flip-flopping like this. And this is pretty evident. There's some kind of flip-flopping polarization electric field. So I know this may be a little confusing. This plot's kind of a lot, but the point is that you have some more evidence here that this is an electrified TID, and not only that, that it's pretty significant in magnitude. And depending on the look angle of the radar, again, there's a background field, so the velocities maybe in this case are flip-flopping in sign, but in some cases they might not be flip-flopping in sign. They might be dominantly negative or dominantly positive, depending on the radar. You can see the velocities here are almost orthogonal to the radar direction. So you might not see the flip-flopping like you do on a previous slide, but the point is you're going to see these velocity variations. And ideally, they'll match with the expected TEC enhancements. So let's talk about that some more. So what is causing this? There's some studies that have talked about this. There's some Japanese studies of Gawa et al. 2009 presenting slightly similar geometries, but these were for quiet time events. So we expect this term here, J equals sigma E naught plus E cross B, to be dominated by the E cross B term for quiet time, because the background electric field is not going to be very significant. It's going to be neutrally dominated. And so it's a similar study. It uses GPS TEC airflow imaging, as well as the HF, the medium frequency radar. And they talk about this, and the geometry is a little bit different, but they're showing that actually the power for the radar is enhanced in the regions where the TEC is located. And I'm basically showing the opposite. So, yeah, the power for the radar in this slide is being shown where the TEC is enhanced. So, the opposite you would expect to be in the purple region. You can actually see purple. Like this is pretty much one, but not. It's a pretty positive correlation between the two, whereas these studies saw a negative correlation. So the question is why? And the answer is not fully understood yet. But the idea is that the gradient drift instability is suggested as the source for these plasma irregularities, basically irregularities in the plasma density on the range of half of the wavelength of the radar. And it needs to be orthogonal to the radar's ray path, and the B field must be orthogonal for this to happen as well. So an explanation of the gradient drift instability is here. But basically, you need like a stronger overall electric field for this to be the case, or these vectors to be stronger. And still working on how all of this ties in, but hopefully the geometries will work themselves out here. But yeah, the neutral wind, the main difference between this study and the previous ones are the neutral wind is the dominant electric field driver, and it's also storm time during the event I showed. So the magnitudes are much, much greater because the velocities are great, everything's great as well. Because it's an 89 huge storm event. So let's talk about some quick stuff. I don't know how much time.
You got just a couple minutes. I was about to give you.
Oh, okay.
Yeah.
Good. I thought it was too fast, but it's not. Yeah. No problem.
That's okay.
So this talk presents a story time MSTID event with periods of 10 to 20 minutes and westward. Actually, I presented two events, but periods of 10 to 20 minutes and westward is pretty significant velocities of the ionosphere disturbance itself, not the Doppler velocities of 500 to 1,000 meters per second, which is a very significant MSTID event. This has probably caused higher latitude because of the space weather event that's going on. And so far, studies like this one have focused mostly on quiet time events. Results suggest that the MSTID shown here is electrified as opposed to following the atmospheric gravity wave mechanism. I have presented some evidence for that. The Doppler velocities of the radar match with the polarization electric fields. I've shown a conjugate measurement. I showed the good correlation between TEC and SuperDARN, which you wouldn't expect if it was ground scatter. And more work needs to be done to fully understand the nature of the plasma. So that's all I have.
All righty. Well, thank you very much. It's just the two of us here in the conference room, but certainly those that are online, feel free to pipe up and any questions, or as well any questions here for Ian. Always a little ways to try to remember how to find the mute button for those that are online.
Hi, Ian. May I ask a question?
Yeah, surely. Go ahead.
Oh, yeah. So in some of the slides, I see
Hold on 1 second. Yeah. It sounded like it was like my left here. See if I can get it there. See if that works. Try that again, Shirley.
Hi, can you hear me well? Hello? Can you hear me?
Try one more time there, Shirley.
Hello?
Oh, man. It's- Yeah,
Can you hear me?
I don't know. Yeah, try that out. I'll have to mute here. Yeah, that's not. Yeah, that's not mute here.
Oh, my one.
Yeah. Yeah, go ahead, Shirley.
Anyway, hello. Can you hear me now? Can anyone hear me? I see everyone's muted.
Can you, yeah, we can hear you.
Oh, okay, good. Yeah, I see on some of the analysis, you do a direct comparison of the SuperDARN and TEC, like such as, any plot, in the RTI kind of stuff. Yeah, something like this. A lot of this kind of comparison. Yeah, I know it's very direct and very novel as well. I'm just wondering, are you able to find like any of these MSTID signatures in the 2D map of a higher time resolution 2D map, so that you can, in this way, you can also quantify like the wave velocity propagation as well as the wavelength. But in a 2D map, you should be able, I'm just wondering, firstly, if you are able to identify this kind of waves. And if so, you should be able to get probably more information from the 2D map as well, just to take advantage of the 2D map as well as this kind of visualization. So you can probably get more information or like have a comparison if what is you estimated from here is consistent what you can get from the 2D map of the TC plot as well.
Right, yeah, that is a good point, and I think that's what a lot of studies do, where they just use the 2D map to resolve this instead of what I'm doing here, just looking at the radar. So yeah, I have the animations, and so certainly you could just pause the animations. Not pause, you could just generate a single slide of the animations, like if you just pause it at any one time, you can see like a front here, and then you could basically like find the wavelength and stuff from that is what you're saying, or you could pause it at 2 different times and measure the distances. So you wouldn't have to go through all this like radar, like resolving line of sight velocities and things like that. Yeah, certainly.
Yeah. I'm just thinking about like whether like a thesis you'll be writing or like a publication, it might be to have both kind of realization or so that you can take advantage of each method.
Yeah, that's a good point. And I think it would probably be easier to understand for whoever reading it as well.
Yeah, and that can also tell you like probably how long it how far it propagate and where it originated, probably things like that. Yeah.
The one challenge is I have found that it's a little bit easier to see in the radar plots because there's not just like so much data where you're just looking at like where the data is located. Still, so yeah, but yeah, that's a good point where it's much more intuitive and you see like where the waves are coming from, where they're going, how they get damped out, what direction.
Yeah, exactly. Okay, if as I mentioned, if it's possible to identify them clearly and to match one-to-one from the RTI plot, the SuperDARN observations, if that's possible. At least I think you can probably find a case or two with pretty clear signature in both visualization and then being able to identify that information.
Yeah, and there's other things I can do too. Like when the data is sparse, you can just make the dots bigger. So you can maybe observe behavior that, like for example, the Rocky Mountains really don't have good coverage here, and this, and you kind of get distracted by just how good the coverage is in the West Coast. But yeah.
Okay. If there's no other question, I can ask another one. So you mentioned about some of the electric field mechanism in some of the later slides, like how the electric field can cause. Because traditionally we are observing in ground scatter, but due to this kind of mechanism, you'll be able to observe this in ionospheric scatter. Is that what you mean, right?
Yeah, this is pretty much all ionospheric scatter. Look at the velocity plot there.
Yeah, but I am wondering, like in this scenario, mostly, let me see if I can annotate. Yeah, mostly it's due to like the gradient of TC data, right? Like you have high TC and a low TC. And in this scenario, it looks like the gradient is in the horizontal direction. So you will observe like the north-south, like Doppler shift, things like that. And this could, one thing I can imagine, like the terminal, around the terminal, like on one side you have a high TC, another side you have a low TC, which can probably cause similar like electric field and then the Doppler shift. But yeah, I'm not sure if this is what they mean, or you mean you talk about some other mechanism as well. But what really I want to say is that that's also cases like such as you have mid-latitude trough, like here. So with high TC northward and the low TC in the trough, and also like because of like even without the trough, you have high probably TC due to the aurora region, particle precipitation, and low TC at the sub-aurora region, which can also cause polarization electric field, but in the opposite direction, like this kind of electric field, and it can cause this kind of drift. I wonder in this scenario, of course, the radar beam with the meridian beam is difficult to sense since the direction is directly perpendicular to the radar beam. But in some of the mid-latitude radar, which we have beams more in the azimuth direction, should be able to sense something like this. Without can be a mechanism or something associated with what you're talking about here.
Like you're talking about like a look direction, like
yes, a radar looking direction like this, but the TC gradient is in the opposite direction. Like right now you have high TC. Yeah, but you have a north-south, high TC in the aurora region and no TC in the trough region or sub-aurora region. And this can cause, yeah, I'm just wondering if this kind of mechanism or stuff can associate with what you are proposing here as well. But
so that might be a larger scale variation as well. That's there's no wavy. Yeah, there's no wavy structure necessarily to it, and so that might be eliminated from the detrending that I'm doing here. And in the storm time events that I've shown, the TIDs are generally westwards, and that's supported from, I guess, the literature of the Perkins instability. But I think what you're talking about is like a SAPS depletion region where there's like a low TEC.
Okay, so I see. So basically, you need some instability or some kind of other mechanism along with this to generate a wave structure. Or
what are you saying?
Shelling, this is I was just about to add that I think in this case, the gradients in TEC are moving there. They're like wave, but when you talk about the trough and higher voltage, they're pretty much sitting there as a constant thing, right? I mean, there could be something going on at the border, but it's not like a moving.
Okay, I see. So you do need like a few a pattern like this, like high low, like a wave structure in order to generate. So what's the mechanism behind this?
Before this turns into just a SuperDARN, because I think I'm noticing online it's just mostly the four of us, whatnot, and maybe we'll wrap this up. And, and you guys could
we can talk about it tomorrow.
Yeah,
that's okay.
talk about it.
I see.
We can talk about it, forever, I'm sure.
Yeah.
Okay.
But yeah, before it gets into a more lengthy discussion, if you want to mute your speakers, and maybe.
Oh, sure.
That's fine. Okay. So yeah, sorry. So just to say, we'll wrap this up before it's a much deeper discussion. It seems like there's a lot more things. But thank you certainly, Ian, for bringing it here to the Space VT seminar. And thanks for those who have joined online and are watching this here later on. To those that are still here, thanks, and I guess have a good spring break. And we will be back in 2 weeks. And I can't remember off the top of my head But we do have somebody on tap for 2 weeks from today. So that will end for now.